going to be on something called support vector machines. This is first of the 2 lectures on support vector machines. And this is one of the very successful models in machine learning that was very popular just before neural networks had their comeback with deep neural networks. So, and we will start with something really simple. So we are doing supervised machine learning. Supervised machine learning. And we are doing classification, right? And so again, we are trying to build a machine learning model. So the idea is that we have some kind of training set. So training set looks like, I don't know, it's a couple of vectors, right? So these are attributes or features. And there is a target variable, and you have, you know, second training example, and altogether you have t training examples. And so the features can be any, as usual, the features can be any real numbers. And the target values in here, I have told you when we are starting with classification that sometimes we will use target values that will be 0 and 1. And that was so until the previous lecture. And sometimes we will use the ones that are +1 and -1. So this will be, today will be +1 and -1. So yi is either +1 or -1. And so if you take an example, so you have, let's say you only have 2 variables. One is apartment size, and the other one is price of the apartment. So, and then we want the sort of the yi will be, the target variable will be, I want to buy this apartment, this is a good deal, or I don't want to buy this apartment. Okay? So probably this will look something like this. So these will be examples that will fall something like here. They will be minuses, right? Because there will be -1s, and the ones that come here. There will be +1s. And so what we are looking for, we are still going to do, for this lecture, we are still going to do linear discrimination. So there will be some kind of line, or in case of like more dimensions, there will be hyperplane. Okay? So, but here there are only 2 dimensions, so hyperplane in 2 dimensions is a line. So we will be looking for a line that will sort of divide the positive from negative examples. Okay, so here in this case, maybe this one is a good one. Okay, and we know that basically the line is defined as simply as a linear combination of features. So we will have a couple of parameters. So basically, if you are looking at your hypothesis space, okay, so hypothesis space will look like basically you will take some vector x, and then you will basically transform it to okay, let's do this form today, and you have So basically you have attributes. Right now we don't have the trick with intercept for reasons, so that I keep you on your guard when we have and when we don't have intercept. So we don't have a column with intercept, so we have to introduce the term that shifts the sort of line around. Okay, so that's this B. And so we have parameters that will be vector theta and number B, and the function will look something like this. So this will be our space of hypotheses. And so once we get what this does is it assigns, every vector that gives it number. So what would we do with the number? Well, usually what would we do in this case? We would just look at sign of this number and assign +1 or -1 based on the sign. Assign +1 or -1. Okay. Any questions so far? So now our goal, okay. So again, we will have lots of, in this lecture, we will have lots of simplifying assumptions. One of the simplifying assumptions that we will have is that there is actually a line that will divide all positive examples from negative examples. Okay, obviously in real cases, in real life scenarios, this is usually not the case. Usually we have trouble finding such a line, so you have some outliers that would go into one or the other category. But for now we will assume that there is such a line. So our task is to find linear discriminant, which is basically the function H from this set of hypotheses, so that the training set is classified. Okay. So I require that there is a. So I'm not interested in the hypotheses that would not classify the training set. This will simplify later our thinking about, now at least I know that the training set, the training error is 0. Okay, so I don't have to. This is something that basically replaces the error fraction. Okay, because now I'm saying I'm not interested in anything that has error worse than 0. Okay, so basically you want to, if I write in the notation that I have introduced on the previous board, then I want to basically find vector theta and this shift coefficient will be so that for all training examples, sine of H theta B X I is equal to yi. Does it make sense? So in other words, I can write this actually in a little bit nicer way. So this is the same as writing. So basically the H theta B X I is simply Xi transform theta minus B. Okay. And then so sine is not a nice function because it's not, it's not continuous. It changes from 0 to like between -1 and +1. I don't like this. So I will instead do, so if this is negative, I want I want yi to be negative. If this is positive, I want yi to be positive. Okay? So this means that I will do, what I will do, I will multiply this by yi. So what happens? If yi is positive, then positive, it will be greater than 0. Okay, altogether. If yi is negative, then, and this is negative, this will be greater than 0. And if it's smaller than 0, that means that these things are opposite each other. So this condition is equivalent to this one. Okay. So now I have pretty much defined my machine learning model. So the question is, how do I solve something like this? How do I find such parameters that I need?
Gradient descent.
We use gradient descent, but here this is going to be difficult because we don't have a clear error function. We want error function to be 0. Okay, so
Linear programming.
Linear programming. So let's do linear programming. That's the other. That's the only other one that we have. So, how would linear program look like?
Okay, we have to define some function that we want to minimize or maximize.
Let's keep that on the side. So we want to have some. Probably want to have a constraint for each case. Okay. So the constraints will probably have something like x1 transpose theta minus b times y1, and like we want to do something. We don't know what to do with that. Okay. So, but we know that this should be positive things. So let's write this way. So this will enter into our restrictions. Okay. And so what I'm going to say, if we want something to be greater than 0, because we want those to be greater than 0, but linear programming only gives you greater or equal. You don't want greater or equal to 0, because then, like, I could set this to 0 and this to 0, everything would be 0 and it would be satisfied. Okay? So I don't want that. So I want to have some kind of constant that will tell you, okay, I'm at least that much from 0. Okay, this can be as low as you wish, but it has to be something greater than 0. So I will introduce something called delta. And I will say all of those should be greater or equal than some delta. So now I have to say, okay, obviously I want to find parameters theta, b, and I want to find actually delta. Okay, that will be common trick in these linear programs is that if you don't know how to do something, you introduce new variables that will help you, that will somehow fix all the stuff that you can't do. So we want to find theta, b, and delta, and so now we want to maximize something or minimize something. So what would we maximize or minimize?
Delta. We want to.
Yes, that's exactly what we will do. So we will maximize delta so that all these conditions, so subject to, so that all these conditions are met. Okay, this is perfectly good linear program. Okay, so basically what I'm saying is I want these to be as far as possible from 0. I mean, if I can choose, why not? Why not as far as possible from 0? what happens next? So you get the answer from this. You have a couple of options that you can get. You can get negative delta. What does it mean if you get negative delta?
It's our data are not linearly discriminatable, or
So there is the data cannot be linearly discriminated or classified as a linear discriminator, or that there is no consistent. It's also called consistent classifier. So there is no consistent classifier. Okay. So if I get a delta that is negative, I know that there is no solution that I'm looking for. And so if I get delta 0, I know I will never get delta negative. Why? Because I can always have 0. Okay? Because if I set all thetas and all b's to 0, I will have this 0. So this will be at least 0. So it will be something greater than 0. Then I know that there is a linear discriminant that sort of is consistent with my training set. And if I get 0, then I know that it's wrong. So now there is one mistake in here. Let's see whether you can spot it. There is one pretty big problem actually with this linear program.
It is not linear.
Why wouldn't it be linear? So because it has to be linear in variables that we have, right? So let's look at what variables we have. So we have thetas and b's, right? These are variables. This is variable as well, okay? And nothing else. Like all of these are constants. Because we are assembling this linear program for a particular training set and then putting it into solver. Okay?
So if it can find parameters with some delta, it can also find some parameters for bigger delta, always.
That's exactly what I was aiming at. So basically, if you have, let's say you find parameters that will give you delta equal to. What happens if you multiply all parameters by 2? You get delta equals 4. You multiply it by 2 again, you get delta equals 8. So if you are trying to maximize delta, you will just go out of bounds on everything. Okay? So that's a problem. And so one typical problem that how this can be solved is that you say that norm of the vector, or maybe sum of the theta I will be 1. So you say, so this is an arbitrary condition. We like we like this type of condition, but basically if you sum all theta i's, you get 1, and that will pretty much limit everything to. This will pretty much limit everything to some scale, and then this thing that that we go out of bounds because you can increase delta by simply multiplying everything by some constant doesn't work anymore. Okay, so this is something that you can do, but this also gives us some idea that this may not be the best thing to do, because, I mean, why maximizing delta? So obviously, if you look at the picture over there, so, I mean, this is not the only line that fits the order, okay? So you can also use, I don't know, you can use maybe this line, or maybe this line. Like all of these satisfy my basic condition that it should discriminate perfectly training set. And usually, if you have any linear discriminator, there will be a couple of ways how to do this. I have just chosen something that maximizes the parameter delta, which I have no idea what it does. So I'm fixing on one of those hypotheses. I'm discarding all of the others, but I have no. I mean, delta doesn't have actually any reasonable geometric interpretation or anything like that. So I'm pretty much choosing a hypothesis based on what is convenient for me computationally. So that's not very good. So the question is whether we can fix this somehow and whether we can replace this delta with some parameter that will have some meaning in my learning system. So any suggestions what the good condition would be? How to limit, how to get
I guess we would like to have the distance to the closest points, like not too close.
Okay, that's actually a good idea. So basically, what's wrong with this yellow hypothesis here is that it goes pretty close to this plus and pretty close to this minus. And if I assume that my data contains errors or something like that, if I have a hypothesis that goes very close to these examples, then I am very likely, if I get another example that will sort of have a little bit higher error, then it may just jump over the line and get misclassified. Okay? So, at least intuitively, and we will see later that it's actually a good idea generally, we would like to keep hypotheses that actually look like the one that I have first drawn. They are far from all the training examples, as far as possible. Okay? So this is what we will do next. So the idea here that we will be using to get linear discriminant for which training points are as far from the hyperplane as possible. Okay, so I think the first thing that we need to solve is that we need to actually be able to compute the distance of a point from a line, from hyperplane. Okay? Who knows how all this is done? Couple, or one. Okay, so I'm going to try to give you some idea of how this is done and how this is actually related to what we are doing. So I have this hyperplane, okay? So obviously I will be drawing everything into dimensions. So here is some hyperplane. Here is some point, like this is a 0 point, okay? Reference. And so I have this point here, which I call x. Okay, so this is my feature vector. And I want to know what's the distance of this feature vector from the hyperplane. So how do I do that? So basically one way of looking at it is that what I can do is I can look at some other point P that is on the hyperplane, so let's say it's here. Okay? So this is hyperplane, maybe capital B. And this is point small p that is on the hyperplane. And so I can obviously compute this distance, right? I can compute this vector. Because this is simply, so x is a vector, p is a vector, and this thing is x minus p, right? But where is our distance b? So where is our distance d of a point from the? I can do that in a couple of ways. One way would be I'm actually looking for a point P that is small, that has the smallest distance. So I could compute the distance and then compute derivatives, and I would actually get the same result. And I'm going to show you some geometric interpretation how to do this. So basically what we want is if you drop this, so this is a perpendicular line to the hyperplane, right? And then you basically want this distance d. So another question: how this is related to our vector? So this plane P is defined by what? By some parameters, right? By some set of variables theta and some vector theta and some term b. Okay. So basically, plane P, hyperplane P, is basically defined as a set of points that satisfy that P of theta is equal to B. Okay? So this is a dot product scalar distribution. Okay? So this is a dot product. It's the same. This is the same thing as theta transport P. The theta transport P. Okay. So this is my hyperplane. So this defines all the points, and I want to sort of drop this line and get this point here. So what's the okay? So I wanted to ask. So if I take theta is also vector, okay? So what would be how this vector would be oriented towards the plane, towards the hyperplane? You can draw theta as a vector.
It would be somewhere inside the plane. I mean,
What do you mean inside the plane? So let's say this line goes through the 0 point. So that really means that this b is 0. Okay, to simplify things. So then I'm basically saying the dot product of my vector theta and my point P should be 0. What does that mean in geometrical terms?
Theta is perpendicular to
That the vector is perpendicular. Okay, so the vector theta, if I let's say start drawing it here in this point, looks something like this. And basically what I want to do is I want to sort of one of the Ludwig ways of looking at it, I want to sort of project this vector to this vector theta, and if I do that, then I will get a vector that is of proper length d. Okay? Okay, so how do I do that? So how do you project the vector that is, there is this vector px, right? How do you project it on theta? How do you do projection? Now you simply do again, dot product, okay? So So you get something like P vector Px theta, and then you have to divide by size of the vector theta. And that's basically the size of the projection. Size of the projection of size of the projection of vector Px onto theta. Okay. So another way of looking at it is that you can also look at it. I mean, if you knew this angle here, which one? I think this. If you knew this angle, okay, so then there is a standard. It's called. You actually learned this in high school. It's called cosine theorem. Basically saying that you get that basically there is a connection between this line and the size of this thing and this thing because there is a right angle here. Okay. And so if you write this in a stronger, but you learn this in 2 dimensions. So if you write it as in a multi-dimensional space, you get something like that. If you take vector theta and vector px in this case, okay, and you take dot product of those. And this is basically size of the vector theta times size of the vector px time cosine of this angle alpha.
What exactly is the vector px?
Px is simply vector x minus vector p. So that's the line from p to x. Okay, so if you start from this, then if you want to know, because what we want to know actually, okay, so what we want to know this d. So this d is what? This is px times cosine alpha, right? So this thing is d. Okay. So basically, if you take and divide this by this number, then you get over size of the vector theta. And this is basically d. Okay, that's another way of looking at it. So basically you have this particular term. So this is basically the distance d, except that it has a sign also. Okay, so if it was on the other side, it would be negative. And so if you wanted the whole projection vector, then you would also multiply this by something like this, which would give. So this is the size of the vector, and this is its direction. Okay. Any questions? Any questions about this? I am very sure that I didn't explain it very well at this point. So who thinks understands this? Okay, so other people, where is the problem?
For example, what does it mean? The size of the projection of px onto theta.
So the projection is simply if you have like a vector and you want to project it in a vector, you simply take, so this will be the projection of this vector on this vector. Okay, so this is what we actually want, right? We want to project this vector onto this vector to get basically vector of size of which is this particular thingy. Okay? And so how do you get the size of this? Well, we know from our high school education that this is simply from the definition of cosine, right? We know that this distance is simply distance of this vector times cosine of this angle. Is that fine? So that's great. So now we have this theorem that basically connects definition of cosines to dot products. So maybe you haven't seen this before. This is actually something that you have seen in high school very likely for two dimensions. And this is just how to write this for multiple dimensions. Okay, so far everything is clear? So we know that this part is our distance d. Okay? With caveat that it might be negative. If it goes in this direction, okay, then projection will be sort of negative. This angle, it will work out so that it's really a negative number. So it's not distance per se. It's a distance with a sign, where sign basically tells you whether it's on the left side or on the right side of the particular vector. Okay? So, everybody clear that this is the term that we want? Okay, so now we only do simple transformation. We divide everything by this, size of vector theta. So we get that this distance is this thing. So if we wanted to just have a distance with a sign, we have it. If we wanted to have the whole vector, the whole projection, we also, because this is just a number, it's just a length. So I need to give the vector direction. And the direction is basically the original vector that I am projecting to, but I need to I just want to have just the vector that I'm multiplying by, I want it to have a unit length. So I divide by the size of the original vector. Is that clear so far? Who understands this? Good. Okay, so let's go. So we have the distance d that we want to compute. Okay, so distance d is equal to vector px dot product of vector px with theta divided by size of vector theta. Okay, so that's just written from here. So what is vector px? That's what someone here asked. Well, it's simply just x minus p. Okay, vector x minus vector p. So let's write it that way. So now, what is this? This is just a, vector is just a set, like a sequence of numbers. It's also a sequence of the numbers, and we are basically multiplying first number with first number, second number with second number, third number with third number, and so on. So if we are subtracting one vector from another, then I can take that subtraction and get it out of this. So basically I can write this the following way. I can do dot product of x this theta minus, okay? So this is nothing special, it's just an algebraic transformation. Okay. So now, what is this? I mean, right now, everything looks fine, except I have chosen some mysterious point P that somehow has to do something with my distance. So the question is, does the computation actually depends on the choice of the mysterious point P? And the answer is no, because definitely my hyperplane on which point P is located is defined in such a way that basically dot product of P and the vector theta is constant B. So regardless of which point P I choose on the hyperplane, I will always get a B for this. So what I am getting is that the distance, which also contains the sign that I am on the left side or right side of the whole thing, is simply x theta minus b over divided by the size of the vector theta. So this is what I will need. Okay, so now coming back to our original idea, the idea was basically find a classifier so I want to find a classifier that has the highest, that has the highest distance of every point in the training set from its hyperplane. Okay, from the corresponding hyperplane. So, and this has a name. It's called classifier with maximum margin. Okay. So the idea is that the margin is something, some space where you cannot write anything. From the grammar school. Okay. That is, yeah. So basically, I want to have some kind of protective area around my hyperplane where no training point gets, and I want this protective area, this margin, be as big as possible. Okay. So basically, I want to. If I'm doing this in a spirit of these linear programs, so I want to find parameters theta and b, which maximize, and I'm just writing this minimum over all i's of distance of xi, yi to x theta minus b, okay, which is my hyperplane. Something like this. And also, I want all points should be on the right side. So there shouldn't be, so all the points should be not only as far as possible from the hyperplane, but they should also be on the correct side of the hyperplane. So now, using what we have derived, yes?
Don't we have to constrict the size of that at V1 for this to work? Because when we were computing distance, then
Distance is this is a good question because it's related to what we have done before. Because, I mean, every hyperplane can be written in several different ways, okay, with different sizes of theta and vector theta. But the distance that we have computed already takes this into account. Okay, so basically, we can rewrite this, okay, because we now know that this thing, okay, is simply theta x minus b over size of theta, and we want absolute value because we have this. Well, actually, we don't need absolute value because we also want all the points to be on the right side. Really means that theta x minus beta is greater than 0 times y. We already established this. So something like this, we want to make this into a linear program. So this won't actually be possible. We will actually use something very similar to linear programming called quadratic programming. And basically quadratic programming, the only difference between linear programming and quadratic programming is that the function that we are optimizing can also be a quadratic function. Okay? And other than that, all the constraints also needs to remain linear functions. So the only thing in quadratic programming, the only thing that we are allowed to do, we are allowed to use quadratic function with a quadratic function in as a parameter that we are optimizing. So we have this. So use quadratic programming. And so I have this first formulation, but it has maximize a minimum, okay? Because basically this says, okay, I'm going to look at which point is at minimum distance, and then I'm going to choose the parameters that will maximize the minimum distance, okay? But that's not really something, I mean, I can only maximize something or minimize something. So, but we already have any idea how to do that? Like what we do when we can't really write something in a linear program or quadratic program.
so we make a new variable that will be distance and
Exactly. So we actually make a new variable. Which will basically be something called delta, and this will be basically size of the margin, okay? So, how our program will look like? So, you should also obviously find theta, b, and delta, okay? So, these will be our variables. And you want to maximize delta. And then I will take, so for each training example, there must be two conditions met. One we already had. So basically the point must be on the correct size, on the correct side. So that was yi x I theta minus b, okay, should be greater or equal than 0. That should be good enough. And then also I want to compute the distance, so the distance of that point to my hyperplane, according to what I computed before, is xi theta minus b over this thing. But it has also a sign, okay? So I would want to do something like this, should be greater or equal than delta. It should be. So how do I get rid of this? How do I get rid of, I mean, absolute value is not something that is a lot. It's not a linear function.
Split it into two cases.
Sorry?
Split it into the two cases.
One possibility, or the other one, I can simply multiply it by yi. And that actually gets rid of this condition, okay? Because I know that if I want this thing to be positive, I should simply multiply it by yi. So I will simply do this, yi times this thing. And then I can get rid of this condition because it basically states this is weaker condition than this one. If this is something, if delta is greater than 0, and this holds as well automatically. So I can get rid of this. Okay, and I also want to limit, to avoid the problems that we had before, although this is not, so this is not crucial. I mean, you remember we also previously limited the size of this vector theta, okay? And we can also do this here. It's not completely crucial because now, like, all our computation actually, has this theta in here. So that's not that big deal, but it's good. It's actually good practice if you have an optimization problem. If you can make it so that it has less ambiguous solutions. So basically, if you can, because this has many solutions, if you don't put this here, and if you can make it so that it has less solution or one solution, that's much better for the algorithms that actually try to find the solution. So this is a good practice to have this here. Okay, any problems with that? Is that a quadratic program or a linear program or whatever?
Computation of the size of theta is not linear.
Okay, so yes, so that's one problem. So this is actually problematic because this is something like sum of theta j squared, and doesn't matter whether it's square root because it's, so basically this translates to this condition. Not linear, right? Any other problems?
We are dividing by that.
Sorry? We are also divided by this. Okay, so this is, to make this more apparent, I can take and I can multiply everything by the size of theta. So instead of this, I will have something like this. And so this seems like, you have delta times theta. That's not a lot, because this is not even linear, and this is also multiplied by another unknown variable, right? So this is like that's completely out of the question to have a condition like this. This part is linear. This part is not. Anyone sees at least the way out of this?
Well, that normalized is 1, right?
Yeah, this is the data normalized this one, so we can actually, get rid of this. But so the only remaining problem is actually here. So how do we deal with this problem? Any ideas?
A new variable.
Introduce a new variable, okay, no. Not this time. It's a good idea, it's always a good idea to introduce a new variable, so. Any other suggestions? So, I'm obvious that this is not a good condition, right? We don't, we could, in the previous task, we have sort of said maybe we can replace this by, simply something that is equal 1, but then it will pop up here again. So this is not a good thing. And again, maybe we can, forget about limiting this, but if we stop limiting this, then this will appear here. So I will do a following trick. I will get rid of this condition and replace it by 1. Because this is, one thing that is nice about this is that by just putting theta, the size of theta equal 1, I got rid of this particular thing, okay? So I want to sort of get rid of this right side here, but I want to do it in another way. So one possibility is that I will do, and I will, instead of saying that the size of theta will be equal 1, I will say that delta times size of theta will be equal 1. Okay? So let's try to write this down. So I have find theta b delta maximizing delta such that yi times xi b minus theta, xi theta minus b yi times xi theta minus p is greater or equal 1, because I will say that, so that's obviously for every training example, and then also I want to have, now I will have size of the theta times delta will be equal 1. That's my condition. So, was that a good idea? So I'm checking, so now I'm starting to limit, I'm still limited to one solution, okay? Because there is only one solution to maximize delta, or like a small number of solutions, so I cannot scale theta in an arbitrary way, but I've tied this size of theta to my size of the margin. I can do that, right? It doesn't matter which scale I choose. And what happened is that, delta and theta disappeared from here. This is a nice linear condition. Any remaining problems?
Well, the
Well, this is all, I mean, the problem still stays here, okay? This is like the quadratic function times delta. So, what's next? Any ideas?
I guess we can minimize that or normalize or something like that.
That's the right idea. So, so we are maximizing delta, okay? But delta and theta are variable, and size of the theta are variables that are tied together, okay? The size of theta, the large delta, since they should be like their multiplication, if I multiply them together, they should be, their multiplication should be 1. So that means that the higher delta I get, the lower theta I should get. So instead of if I have this condition, instead of maximizing this delta, I can also say, and it's equivalent thing, to say I want to minimizing theta. And I can do theta squared. So this will be basically sum squared. Right? It's just, if this is a positive, this is non-negative number. So if I'm minimizing this non-negative number, I can also minimize this non-negative number squared, and it's the same thing. Okay, so this is allowed. We are doing quadratic programming. This is perfectly fine. But this is still here. So what to do with this?
Well, we're not using delta anywhere anymore.
We are not using delta anywhere anymore. So and not this condition doesn't actually contain delta at all. So I don't need to actually compute it. And simply, get rid of this condition and get rid of this requirement. And this is my final quadratic program. So I want to find parameters theta and b so that I minimize the size of this vector such that all of these conditions are met.
Can you just repeat the idea behind discarding this last condition? Because it just happened too fast for me.
Okay, so where is delta? Where do you use delta?
Well, nowhere except the last condition.
Except the last condition. And the last condition is the only thing that actually, the only thing that this condition is used for is to compute delta. So if you don't want to compute delta, then we don't need to, right? So we decide that we don't want to compute delta, then we can get rid of this condition altogether, because we don't need it. Okay, so this is it. So we have by series of steps that introduce this margin variable, introduce this idea of finding the maximum margin classifier, and trying to formulate it as a quadratic program. We came to this is actually quite non-trivial quadratic program. Okay, because it doesn't have it doesn't have distance in it anymore. It doesn't have a margin in it anymore, but it still not maximizes margin of the classifier. Okay, so this is the way how you can compute the maximum margin classifier. So in the next lecture, what we will do, we will quickly review this, of course, at the beginning, and then we will go and introduce additional tricks to make this something that is called support vector machines. So this is not it yet. It's we are still like half of 2/3 of a lecture before we can call this a support vector machines. And part of this will be to give idea of how this computation, what the actual parameters that you get from this mean. But there will be also additional advantage that we will be able to extend this. You remember generalized linear regression? So we will be able to do this within this framework of support vector machine, but in much more efficient way than in the case of generalized linear regression. So that's for the next time. Thank you very much.